Hello, and welcome to our next lecture in elementary statistics at Dallas College using ALEKS. Today we're looking at chapter 3.1, Measures of Center. Here are the objectives for the course. I'm not going to read through them. You can hit pause. This is a good list. I always start and end with the same list, so you can always check your knowledge base. The mean of a data set is what we call a measure of center. And the idea here is if you imagine each data value to be a weight, like you see at the bottom of the page here, then the mean is the point at which the data set balances. You can think of it as the fulcrum for this weight, etc., and where it's going to balance out. You are familiar with this mean. This is what we call an average. You've probably figured out your average test score or averages in the past. Remember that a population consists of an entire collection of individuals about whom or what we're studying, and a sample consists of a smaller group drawn from that population. Again, like for example, maybe our population for our study is concerning is all of Dallas College students, but it's not practical to survey them or observe all of them, so we might pick 10 classes, and those 10 classes become a sample, which we draw conclusions or inferences towards our population. The method for calculating the mean is the same for both samples and populations. However, the notation is different. For a population mean, we use the Greek letter mu, and for a sample mean, we use a symbol called x bar. It's x with a line over top. Now remember, this data point in a population is called a parameter. All data for populations are parameters, and all data points for samples are called statistics. So statistics specifically represent data for a sample, and parameters represent the population. So this should be pretty straightforward. When we're calculating the mean, we simply add up all the values that are represented, all the responses, and then we divide by the number of responses there were. This symbol here is a sigma, and it just represents the sum of all these values, of course, and then our mean is the sum of all those values divided by how many there were. If these were test scores, you would add up all the test scores and then divide by the number of tests you had. And you can see it's the same formula whether we're dealing with, again, population or sample. So let's try one here. During a semester, a student took 5 exams. The population exam scores are 78, 83, 92, 68, and 85. Find the mean. It's a good time to hit the pause button and see if you can calculate that. So again, we're just going to simply add up all of those numbers, divide by 5, and you can see we get 406 over 5, which gives us a mean of 81.2. Note that we rounded the mean to one more decimal place than the original data. This is generally considered a good practice whenever you're calculating information in statistics to actually, whatever the data points, number of decimal places, to go to one more when you're calculating the mean. It's often impossible to compute a population mean, and this is really, it's about logistics, right? To try to get a response from even every student at Dallas College, which is a finite number, but a large number, it would be hard, and it would cost a lot of money, it would cost a lot of time. And so instead we draw a sample and use the sample mean as an estimate. That is, we use x bar we calculate x bar and then use that to estimate mu. So we look at the statistic x bar, the mean for a sample, and then try to extrapolate that to imply what the mean of the population is. Of course, when we're doing that, it's very rare we would have an exact amount that matches the population mean, and so we either get an overestimate or underestimate. So here's an example of that. There were 440 players in the National Basketball Association in a recent season. The actual mean height was 79.2 inches. But if we took two different samples of 5 players, as we see here, in one of them, the first one, we get an average or mean of 80.2, which is an overestimate. And in the second one, we get a mean of 78, which is an underestimate. So, I mean, this is common, but they're close enough that it makes a lot more sense to spend less money, less time to do sample means instead of trying to figure out how do I actually coordinate a population mean. The other thing, though, we can do to try to ensure that our sample mean or data point is relatively similar to that of the population is simply to take a larger sample. So if we did samples of 20 people instead of only 5, we would probably find less variation in this. There's a misconception about the mean. I don't know that this is true across the board, but some people think like the mean has to be a value that could be a response given by a subject in a study, etc. But remember, a mean is a calculation, so it could be a value that could not possibly appear in the data set. So here we have 5 means, 78. These are 5 exam scores, 83, 92, 68, and 85. When we take the average, we get mu, or the population mean, is 81.2. Most exams probably have scores that are whole numbers, so 81.2 is not a typical data value, but it is certainly reliable here. Another good example for that, I think a better example, is when people ask like the number of children you have, and then the average number of children across a group is like 2.4. Well, of course, no one has a 0.4 child, but we can see why the average would be a decimal instead of a whole number. All right, let's look at another measure. Median is another measure of center. The median is a number that splits the ordered data set in half, exactly in half. Half the data values are less than the median, and half of the data values are greater than the median. The procedure for computing this depends on whether we have an odd or even number of observations. If the number of observations, the median, is the middle number, and if the number of observations is even, then we take the two middle numbers, the numbers that are exactly in the middle, and find the average of those two. Now, when I say this, I'm talking about ordered data. So the first thing we have to do is put our data in order from smallest to largest before we find that middle number. During a semester, a student took 5 exams. The population of exam scores is 78, 83, 92, 68, and 85. Find the median of the exam scores. So go ahead, hit pause again, and try this problem. When you're ready, hit play and find the solution. So the actual answer here is 83. The first thing you do is arrange them in increasing order, and then you just pick the middle number. Let's try another problem. Again, go ahead and hit pause and try this problem. And then when you're ready, hit play again. Example 2. 8 patients undergo a new surgical procedure, and the number of days spent in recovery for each is as follows. 20, 15, 12, 27, 13, 19, 13, 21. And we're asking you to find the median number of days in recovery, which should be 17. Again, remember the first thing you're going to do is put these all in order. Then since we have an even number, you are going to average the two middle even numbers, which is 15 and 19. And the average of 15 and 19 is 17. So the median time spent in recovery is 17 days. So your book has explicit instructions for how to use technology, whether you're using Excel or TA84 or other technologies in class. You can go to your textbook. This is the back of each chapter and section, and it gives you special instructions for how to use that piece of technology. One of the things about, or the reasons why we have or use both the mean and the median, is that one of them, specifically the mean, is more influenced by extreme values. What do I mean by this? If we have really high values or really low values, this can often skew the value of the mean a lot more than it would the median. So the mean is more influenced by extreme values, very large or very small, than the median. We say a statistic is resistant if its value is not affected much by extreme values, by outliers, as we sometimes call them, large or small. These are just data points that fall outside the majority of where the data is. And so we say a statistic is resistant if that statistic, whatever it is, in this case median, is not affected as much or by extreme values, large or small. The median is resistant, but the mean is not. So here we have 5 families with annual incomes of 25, 31, 34, 44, and 56,000 respectively. Okay? So find the mean and median of those 5 income levels. One family just won the $1 million lottery, so their income increased to $1,025,000. I want you to use this new number for that family, for the $25,000 family, and again calculate the mean and the median. Okay? When you've done that, think about what those values represent, and then hit play again. Here we see the mean of 38,000 and the median of 34,000 in the first 5 numbers before the lottery win. But notice what happens after the lottery win. The mean has jumped up by $200,000, where the median has only jumped up by $10,000. So can you see a reason why we might want to use mean at some times and median at others? Okay. So if we have a data set that has a lot of outlying numbers that may be valid, may not be valid, but we're concerned about that, we might choose to use the median as a measure of center because we have these big values that are not representative of everyone in our population. So another thing we can tell is sometimes with the mean and median, we can tell the shape of a data set. The mean and median measure the center of data set in different ways. When the data set is relatively symmetric, the mean and median are going to be relatively equal. As you see here, they're both in the center of the chart. When a data set is skewed to the right, there are large values in the right tail. That pulls the mean in that direction, to the right. The median is resistant, so while the mean is not resistant and is being pulled to the right, the median pretty much stays in place. For a data set that is skewed to the right, the mean is often greater than the median. Notice for skewed to the right, the mean is to the right. When a data set is skewed to the left by similar arguments, the mean is skewed to the left. The mean is pushed further to the left than the median would be. So what is a better measure of center, mean, or median? There really isn't one that's better in all cases. You have to look at your data. And again, if you have a data set for your study that has a lot of outliers, then you probably want to use the median. The advantages and disadvantages of both are identified here in a little table. And so this might be something you think about when you're doing your study and trying to figure out what are the key statistics that represent your data most effectively and honestly.